So before we get into two-dimensional collisions, I wanted to go back and do a couple of more examples of one-dimensional collisions. So in this example, we have a 12-gram wad of sticky clay is hurled horizontally at a 100-gram wooden block. After impact, the block slides 7.5 meters before coming to rest. If the coefficient of friction between the block and the surface is 0.65, what was the speed of the clay immediately before impact? So again, it's kind of difficult to imagine these situations just by reading it, so it's a good idea to draw a picture. So again, we have a wad of sticky clay. It's being hurled horizontally towards a block. And once they come in contact with each other, then they go across a friction floor that has a coefficient of 0.65. Okay, what we want to know is the velocity that this clay has right before it collides. Now, you can already see that this is going to be an inelastic collision, a perfectly inelastic collision, meaning that they will stick together. So, this problem actually needs to be worked backwards. We can see that if we have a coefficient of kinetic friction, we know the distance that it travels before it comes to a stop, then we can actually calculate the work done by friction. Again, I know that my change in kinetic energy is going to give me my work done by friction because that's the only that's the only force slowing it down when it reaches that friction part. So again, my change in kinetic energy is final kinetic energy minus initial kinetic energy is equal to my work done by friction, in this case, mu mg times r, our distance traveled. So we know that the block and the object are going to travel until they come to a stop. I know they're going to travel until they come to a stop, so my final velocity will be 0. My initial velocity is what we're trying to calculate. Again, we're trying to work backwards to eventually get to the velocity at the very beginning. Here, my masses will cancel out. And even if you didn't cancel the mass, you needed to make sure to include here that this is the mass of both the clay and the block. But in this case, it doesn't matter because it does cancel out. Again, our goal is to find our velocity. So this is the square root of 2 mu mg r. Now, I can include this cosine of 180, but that will just cancel out this negative sign I had to begin with. So our velocity should be 2 times our coefficient of friction times, we canceled out this mass, times gravity, I'm going to go ahead and use 10 here, times our distance traveled, which was 7.5 meters. You should have gotten a velocity of 9.8, 7 meters per second. So I labeled this as the initial velocity. Well, really, that's the initial velocity at this point. So if I want to solve for the speed before impact, this actually becomes the final velocity of the first segment. So again, going back to the first segment, I know that at the beginning, my clay has some momentum. The block does not have any momentum at the beginning. And then again, once they collide, they're going to collide inelastically, perfectly inelastically. So they will stick together. Both the mass of my clay and the mass of my block need to be added together, and they will travel at a final velocity v, which we found here. Again, the goal is to get v naught by itself. So that becomes m1 plus m2 times v divided by m1 is equal to v naught. Putting all of our numbers in, remember that you should be using 0.012 kilograms plus 0.1 kilograms times our velocity, all divided by my mass 1, which in this case was our clay. And you should get a velocity of 92.2 meters per second. In this example, we have a 5-gram bullet moving with an initial speed of 400 meters per second. It's fired into and passes through a 1 kilogram block. The block, initially at rest on a frictionless horizontal surface, is connected to a spring with a force constant of 900 newtons per meter. If the block moves 5 centimeters to the right after the impact, find the speed at which the bullet emerged from the block and the mechanical energy converted into internal energy in the collision. Again, with a problem like this, it's difficult to imagine, so it's important to draw a picture. Again, you have a bullet, you have a block, and it's attached to a spring. So we can assume that this situation is going on. Again, what's happening at the beginning is we know that this bullet has an initial velocity of 400 meters per second. Once it collides with the block, it's going to collide inelastically. And this is not a perfectly inelastic collision. So we want to know that speed of the bullet after it has come out of our block. So we want to know the speed of the bullet here. So remember that for inelastic collisions, kinetic energy is not conserved. That means before and after the collision, the kinetic energy is not the same. Now, that's not to be confused with a kinetic energy after you've collided. So we're not talking about before, but we're talking about the energy after our situation. So again, once they collide, I know that the block is going to have some kinetic energy, and that kinetic energy is going to be entirely converted into spring potential energy because it is going to compress the spring. So this will actually help me solve for my initial velocity or the velocity of the block after they've collided. Now this is not asking for this is not calculating the velocity of the bullet, this is simply calculating the velocity of the block. So again, here 1/2 cancel. We want to solve for velocity, so that's velocity is equal to the square root of kx squared divided by m. Now here, the mass you're going to be using is only the mass of your block. So this is 900 times 0.05, again we're using our meters here, divided by 1. Again, our mass of our block. You should have gotten a velocity of 1.5 meters per second. So this is the velocity of the block. Now, the bullet does have the same variables, the same letter b. We're going to label it with a lowercase b instead. So again, I know that this is the velocity of the block after they've collided. So going back and using momentum, I know that at the beginning, my bullet has an initial velocity. My block has no initial velocity before they collide. And at the end, when they do collide, I know that my block is going to have a momentum that comes from this 1.5 meters per second. And my bullet will also have momentum. And this is actually what we're trying to solve for here. So we just need to get it by itself. So move this piece over. And we get mass of our bullet minus the initial velocity of our bullet minus the mass and velocity of our block. And then at the end, divide by our mass of our bullet. So you should get a velocity of 100 meters per second. Now, the last part asks us to solve for the mechanical energy converted into internal energy in the collision. That means because this is an inelastic collision, we did lose energy due to the interaction between our bullet and our block. So what we can do is find the kinetic energy at the beginning, find the kinetic energy at the end, and then figure out what the difference is between the two, and that's the amount of energy that we lost to our environment. So our kinetic energy before a collision is 1/2 mb v naught b squared. And we're going to subtract some energy due to, we'll call it friction in this case. It's not kinetic friction. And what I mean by that is it's not the friction in between the block and the surface. It's more of the friction in between the bullet and the block. Is equal to our kinetic energy of the block plus our kinetic energy of our bullet. Now, here you need to be careful that you do not just cancel out all the 1/2s, because again, the energy that we're trying to solve for, that mechanical energy, does not have a 1/2, so it's not something that you can cancel. But what we can do is we can move this piece to the other side so that it becomes positive, and then move this entire piece over to the other side. And you get 1/2 mb v naught b squared minus 1/2 mb v b squared plus, minus 1/2 m lowercase b v lowercase b squared equals the work done by friction in this case. Again, once you put in all of your numbers, you should get a mechanical energy loss of 374 joules.